Hi everyone. So now that we know how a diode behave in a circuit, we're gonna do a couple of circuit practice with diode first before jumping into the other type of applications of circuits that you can we're gonna explore in the lab. So the rules of a diode is that when there's no current flows through it, if delta V across that diode, right, is less than this diode voltage, let's just use 0.7 in this case, okay? Because that's the ones that we're gonna have in the lab. If delta V is bigger than the diode voltage, you can get up to infinite current, but usually what's going to happen is that you're going to limit that with some resistor or something like that so that you don't have infinite current flowing through it. Okay. So in this case, and then when delta V is approximately the diode voltage, then you have this exponential growth. We're not going to deal with a problem. Maybe we'll have to, maybe in the pre-lab you have like a question on that, but we're not going to actually utilize this for now. It is going to be useful when we think about photodiodes, so with this proportionality thing, but for now, let's just deal with the first two rules in these circuits, okay? I'm going to set up a circuit here. Let's just do something simple, right? You have some battery on this side, and then you have some resistor here, R1. Let's just call this V1, okay? And then we have some resistor going down here, R2, right? And then we have this interesting point where we have a diode. So we added a diode into our circuit. And maybe the other side is going to be connected to some V2, okay? And the question may be, oh, you know, what is V out here? Okay, if we take the V out to be there, okay? Right, we have two voltage sources, two resistors, okay? And the way you analyze diode circuit is a little bit different from when you analyze those without it, because you're going to explore two different cases where first you're going to assume, okay, maybe well, you don't have to do it first. One path is that, oh, the diode is on, okay, and therefore you analyze the circuit when it's on. And then the other case, you analyze the circuit when the diode is off, okay? So you analyze it once doing this, and then once doing that. Okay, I'm going to do the on case first, meaning assuming that delta V across the diode is bigger than VD, or 0.7 volts. Okay, so if we assume that the diode is on, okay, that means this is just a short, basically, but you're still going to get a diode drop across this all the time, this constant 0.7 volts, okay? Right, and let's see what happens when we do that. Okay, so let's do Kirchhoff's law, right? Then we have this, let's do this loop, and we're going to see that maybe the only one we need. Okay, when the diode's on, we get VD, V1, right? We start here, and then you get minus I, let's call this I1, let's call this I2. So the current that's going across this is actually I3, but we actually don't need that because we don't have a resistor there. Okay, minus R1. Okay, and then we have a diode drop across this, right? Because that's the next thing we see. Okay, and then we run into this V2, which is the opposite direction, so we actually have a negative of that. And now we're back in the same place. Okay, so right, so in this case, it's actually pretty simple. Where this I1, right? We can actually just solve this equation for I1 previously. I1 equals to V1 minus VD minus V2, okay, all divided by R1. Okay, that's the current there. And therefore, right, the voltage at that point is actually going to be much simpler because, right, whatever this V2 is, right, V out is going to be a voltage drop above that. So you can calculate what this current is, you can calculate what this is, right? So in the case that diode on, let's just do that. Okay. V out is always just going to be VD plus V2 because you're kind of keeping that constant. I guess we could calculate what this current is, but that's just going to be held constant too. And what's going to happen is that it's just going to force current down R2 in order to make this to be true, because this battery is going to give you a constant voltage source. Okay, so let's do the case where the dial is off. The dial off case. Okay, in that case, in fact, I'm going to redraw this diagram. I think that's enough space, yeah. It's a little wider. Yeah. Okay. Let's do it below, so my screen, my notes don't go too wide. Okay. Give myself a little bit more space to redraw the circuit diagram. So the dial off case, it's the same thing, but it actually simplifies a lot of stuff, because when the dial is off, right, what you can do is basically not connect the circuit to it, right? So somehow this gets disconnected. Okay, you still have V2 here, you have V1 here, you have a resistor going to ground. In this case, you can just completely ignore this side of the circuit, right? Because it's not completed. V out is still here. So in this case, V out is actually just a voltage divider, which is going to be V1 R2, that's a 2 down here, over R1 plus R2. Okay. So depending if the voltage, if the dial is on or off, right, that's going to determine what your voltage output is. And that is determined by basically what is V1, what is V2, right? Because, right, V1 will basically set the voltage here. Let's highlight that here, right, this yellow, right? If V out is bigger than V2 by 0.7 volts, then the diode would turn on. But if it's less, then you have the second case. Okay, so let's put in an example with some numbers. So pick some numbers here. Okay, let's say V1 is 12 volts. V2 is 6 volts. So the thing to check is that on or off, right? And then if it's on, then you already know the answer. It's 0.7 volt plus V2, whatever that number is. So 6.7. If it's off, then you apply the voltage divider equation, and then you get the answer, right? So that's maybe part A of a problem. Okay, so if V1 is 12, V2 is 6, then first we apply the voltage divider here. So we have to have the R value also. Okay, let's say R1 equals to 1 kilo ohm, R2, let's just make them equal to easy calculation. Kilo ohm. Okay, so goes to R2. Okay, so this is just a 1/2 voltage divider. So if you apply this, then you have half the voltage here. So V out is going to be at 6 volts, right? So that's not going to be 0.7 volt above V2. Therefore, in this case, the diode is off. So V out, the answer to V out, you apply the off version of it. So V in, which is 12, right? And then R1 over R2 is going to give you that one factor of 1/2. So you're going to get 6 volt. That's what V out is going to be. Okay. Say we have another version of the same problem, same circuit, but then we lower V2, right? Same, except that V2 becomes 5 volts. Yeah, you can see why I picked these numbers. Okay. So once again, right, the voltage divider is going to give you 6 volts on this side, on this V out. But in this case, right, 6 volt is going to be 0.7 volts above V2, which is at 5 now. Okay, in this case, the diode is on, right? When the diode is on, all you have to do is just say that, oh, well, whatever the V out is, it's going to be 0.7 volts above the battery, the second battery, VD, which is going to be, let's say 0.7 volt plus 5 volts, or 5.7 volts. Okay, and that's the answer already. Okay, and so that's how you analyze these diode circuits. You do the calculations with the dial on and dial off, and then you depending on the voltages that you get, you're going to either have on or off, and then you apply the proper equation for that. Okay, so let's go through some other circuits that's going to be useful. Let's see, I guess we don't go to the Zener dial yet. Okay, so so the first application of the dial is called rectifier circuit. These are basically AC to DC converters. So if you have some, I'm going to give you a little hint, right? So you have some AC going in, but then you want your, this is V in, but you want your output to be kind of a constant V out, right? So this is DC, this is AC, right? You want to convert from AC to DC, you'd use a rectifier. In fact, there's many of these. So in your, let's say you have your little USB charger, there's a rectifier in there. In your power charger, you have a rectifier. There's a lot of rectifier inside other devices also, so that you're converting from your AC current to a DC. Okay, and the power supply you're using in your lab has a rectifier in it. It actually has a pretty beefy one. So let's see what this does. Okay, so this is how we can build this. So you have some AC voltage source, right? So this is some AC voltage source. Okay, and you pass it through a diode first, and then you put a resistor right after it, and then it just connects to ground. Okay, so the diode drop is going to be 0.7 volts. So what happens is that when Vn is above 0.7 volts, right, this diode turns on, and then basically you just have Vn minus 0.7 volts on this side, and let's say you take this as V out, and let's do that in black so it's clear, right? You take that as V out. Okay, in that case, V out is going to be whatever V in is, just minus 0.7 volts. Okay, this is the on case. I'm going to split this. Let's see what happens when we get the off case. Minus 0.7 volt. Okay, that's one case. But when Vn is less than 0.7 volts, the diode stays off, right? Remember, when it's off, it's as if you cut the circuit, right? And therefore, no current flows through this, and therefore, Vout is actually 0. It was off, and this is the on case. Okay, so let's see what this looks like when we plot this, okay? So as Vn goes up and down with this dashed blue line here, hopefully you guys can see that. Okay, and highlight it, right? What's going to happen is that the V out only gets to, is equal to Vn minus 0.7 volts, as you can see here, only when is Vn is above 0.7 volts. So you get the red line here, right, when you get above 0.7 volts, but then you get 0 otherwise. Okay, so the entire negative swing of Vn just gets ignored. Okay, in fact, anything below 0.7 volts gets ignored. Okay, this is a pretty neat way to like basically remove negative voltages in your device if you want, but this isn't really like constant, right? So you know, if you need 20 volts to power your laptop, you don't want it to go up to 20 volts and then drop down to 0, 20 volt, drop down to 0 all the time. Okay, that's gonna not power your laptop up properly. Okay, so if we want to convert AC to DC, we want this output voltage to be more constant. Okay, an easy way to do this is basically to add a little capacitor to kind of store the voltage for a short time. So what you want to do is just add a little capacitor parallel to your resistor load. Okay, and what's going to happen is that as the voltage ramps up, right, charges will get stored here, and then what happens is that when the voltage goes below, these charges keeps the current going, so that you actually still have a more constant V out. Okay, So this is something that you probably learned in general physics, where a RC circuit has a decay constant of equal to R times C, and that's because if we plot, we just have an RC circuit, the decay is basically an exponential decay e to the minus t over RC. Okay. So what will happen here is that instead of the voltage going down right away, it's going to decay with that RC constant again. I'm going to see this on the next plot. Okay, so the voltage goes above 0.7 volts. It follows the Vn minus 0.7, but then when it goes back down, what happens is that instead of turning off right away, it decays slowly. Slowly as in maybe tens of milliseconds. And therefore, instead of having the voltage go to 0 right away, it goes down slowly, and hopefully your AC voltage is fast enough so that it actually ramps back up before it gets to 0, and therefore you have this kind of what's known as a ripple. Okay, these ripples are okay as long as maybe they're in like tens of millivolts. Okay, that's fine. That's within the tolerance of the DC device you're dealing with. But if the ripple is maybe like plus or minus 1 volt, then that might damage your device, and or not powering up enough. We're gonna see this in the lab. So you want this ripple voltage, okay, let's highlight it here, right, to be something on the order of tens of millivolts, but not more than a volt. Okay, but you notice that there's always going to be this 0.7 voltage drop. Okay, and anything beneath 0.7 in the input, right, this blue line here, right, really still gets ignored. Everything that's negative gets ignored. Okay, this doesn't really directly waste power, but what happened is that because if you're blocking the current, basically no power is driven through the device. But you're basically having to double the frequency of your Vn in order to drive the same device. So this is where the next circuit comes in useful, which is the full wave rectifier. Okay, the books has a fancy, diamond shaped version of it. I like this version from a different book because it's easier for me to analyze. So over here on the left hand side, you have Vn, right? There's some AC source. Okay, and what happened is that let's assume that Vn is positive and 0.7 volt above. Well, actually, in this case, it's going to be 1.4. Okay, 1.4 above the above ground. What happened is that, well, if it's positive, it cannot go this way because you cannot drive current backward through this. Okay, that's fine, right? But then it can go through this other diode, okay, which drop your voltage by 0.7 volt. Okay, and now what you get here, right, is that you're at 0.7 volt, and that's what your V out is. Okay, and then the current keeps going through this resistor. It goes around here, it goes up here, all right, and it goes through another diode, which drops it by another. Right now, this is going to be another voltage drop of 0.7 volts, and then now you get back to Vn. Okay, so on the positive swing, what happened is that instead of going through one diode, you have to go through two diodes in order to get back to through the loop. But that's okay. But that's the same thing as your half-wave rectifier. Okay, all right. But let's see what happens when Vn is negative, right? And Vn is negative, right? This is more negative, this is more positive, right? Now in this case, the way you can think about this is that, well, instead of current going in this direction, I'm going to try to drive current going through the other direction, right? Now that you have this, you have the similar situation where the current's blocked this way, but then it can go through this other set of diode, still give you the same Vn minus 0.7 volt, okay? And then it goes through the resistor, right? Should do this in a different color, I think. Go through the resistor, comes back here, and instead of going through this resistor, is going to go through, sorry, this diode is going to go through the top diode in order to reach back to V minus. Okay, so both on the positive swing and the negative swing, you will get the same output voltage, except for the part where you have this kind of jitter where it's between 0.7 volts. Okay, so when your V in is plus or minus, less than plus or minus 0.7 volt, then the output is still going to be 0. Okay, so what the output will look like is this plot below. Right, so let's highlight this in green, so that's not the color that's being used. Right, so as usual, right, as Vn goes up, right, you after it gets to 1.4, because you have 2.2 diode drops, then you would actually have current going through the resistor, and therefore now you would get an output voltage that is basically copy, but lower by 1.4 volts. Okay, that's what V out is. Okay, do that in red, so it's the same color. Right, V out. Right, same thing happened, and then when you get close to 0, it turns off again, just as before. But on the negative swing, right, now the current flows in the other direction on the other path, but it's still giving you this V in minus 0.7 still. Okay, and this V in minus 0.7 will give you a positive swing. It actually flips it upside down. Okay, and the same thing happened over and over and over again, and now you basically have you're basically using both the positive swing and the negative swing of your AC voltage source to produce a positive DC voltage. Okay, well, almost DC in this case. Okay, it's still rippling up and down a lot, right? Okay, so the same solution as before, right? If you want to reduce this ripple, you put a capacitor parallel to the resistor. Okay, and once again, the value of the capacitor and resistor depends on how much ripple you're able to handle. Typically, the larger the capacitor, the less ripple there will be, but then the bigger and heavier it'll be. So that's why if you have something that has a very tight tolerance, you actually have a big capacitor on it, and therefore it actually reduces this ripple situation. And we're going to get to see this in the lab and calculate it. Okay. And so similarly, if you put this capacitor in here, it kind of smooths out with this exponential decay between the up and down swing of your AC source. Okay. All right. I'm just going to cover a couple of more types of diodes. Yeah, 23 minutes. So there are other types of diodes out there that are not just the PN junction. The Zener diode is a PN junction, but it's designed with a special use. It's designed to know so that we know exactly where the reverse bias breakage voltage is going to be. Okay, so remember, this is how a diode behaves on the IV plot, right? So it's 0, right, and then it turns on, right? But then, so this is actually VD. And there's also a negative version of the VD, right, which is, the breakdown voltage. Okay, we can design these diodes so that we have a specific breakdown voltage. And why this is useful is it's actually used as a voltage regulator. Basically, it's a way to make sure your voltage don't get too high and damage your device. Okay, so let's say you have a little 15-volt power source, but then you want just a plus 5 volt on your device. Okay, so what you do is you connect this to a resistor, and through this 1N4733 diode, which has a breakdown voltage of 5.1 volt. Okay, and what this does is that if the voltage is above let's say it gets to 5.2, this becomes a short, and it's basically just running the current to ground, and then basically this turns to 0. Actually, it turns to 5.1, right? Because once it drops below 5.1, it goes back to being a blocking diode again, and therefore it keeps the voltage beneath 5 volt, 5.1 volt, and therefore it's protecting your device from over voltage. Okay, so this is a very useful device. There are also other type of diodes known as Schottky diode. This works on the same principle as a PN diode, but what you do is you replace the P part with just a regular conductor. Okay, what this does is a little diagram here. So you replace the P side, right, with just a piece of metal. What this does is that it has kind of like the half effect of a PN junction. And what that happens is that these electrons that are free to move on your N-dope material will migrate towards the metal, right? But instead of filling out holes that would be on the P type semiconductor, what happens is that they just kind of sit in the metal and they're just kind of moving around randomly. Okay, and this is going to be a thin sheet of metal, and therefore the negative charge actually stays around there, and this still produces an electric field. So this will have some negative charge on it, and then you have some, because these electrons left, right, you have some positive charge here, and this still produces an electric field pointing this way, but the strength is going to be half as much because you're not filling out the positive holes that are in the P-type conductor, P-type semiconductor. Okay, so this actually kind of usually cuts the diode drop by half. So like the voltage drop across the Schottky type diodes are usually about half of what you see in the PN type of diodes. I think I spelled wrong. Schottky diode, not Schottky. Okay, so this is another type of diode that you may see in the future. We're not going to use them in the lab, but just so that you know that they exist. All right, and that's everything we want to cover about diodes. So, and then hopefully next week we will talk about transistors, where we can start amplifying signals from this. Okay, all right, thanks.